Yeah, hello and welcome to our second day of the Digital We Days. My name is Vivian Neuberger and I will moderate this webinar today. Today's topic of this webinar is a brief overview of the SPE system with PoE, reference design concept and key EMC challenges. Also, I would like to welcome Adrian Stirn. He is technical lead for EMC laboratory, and Heinz Zenkner. He is expert for application engineering. Yes. SPE and PoE simplify connectivity, but how do your circuit blocks and EMC demands shape your design? Let's break it down. Stage is yours.
Oh, thank you very much. Quick introduction. Yeah. Also, hello to everybody. We have only, 30 minutes?
30 minutes only.
Oh, yeah. We have to speed up. Let's start. I will skip the agenda. That's only for your reference. You can download the slides later. There's a lot of information inside. I cannot go through all of this because this would last too long. So let's start with the technical background. What is the idea about single pair Ethernet with power over Ethernet and the data transmission over these wires? Sorry. Yeah, the idea is to have the signal and the power over only two wires. As you can see here on the slide, we have here a transmitter and we have a receiver. And between of them, we have only a twisted pair cable. This might be shielded or unshielded, but it's not the key point now. The idea is that we decouple. We decouple the signal capacitively, and we decouple the power by impedances, by inductors here. So the idea is to have the power from the transmitter to the receiver and the signal from the transmitter to the receiver over these two single wires. So this is one technical option to show you the principle. You will see later on the real design we have done is a little bit different, but the key point is shown very clearly here. So it is a little bit different than you might know the concept from the single pair, from the power over Ethernet with the Ethernet. This is one example here. This is the gigabit Ethernet, where you see we have 4 channels. And here we couple the energy from the hub here to the powered device via the center tapping of the transformers here. So the signal here is galvanically decoupled, but by inductance, so inductively decoupled. And we have here in the center of the transformers here, the energy which goes in common mode over this line and is received again and decoupled in the center to the PD, to the receiver. Whereas here, which I have shown before already, the whole thing is let's say, non-decoupled, not galvanically, but via high frequencies, the inductors here, not to impact the signal. This is the idea here. So the concept is not the same. There's a huge difference between. So the hardware topology of the system. Now you see the real design, how it is solved by us and our reference design. You see here the power source equipment, and you see here the powered device. So on the left-hand side, we have here, coming from the cable, transient protection. This is limiting overvoltages. Then we go to a common mode choke, which decouples here the signal and the power. Then we have here the power incoupling. But you see, that's a common mode choke, which is, let's say, used vice versa. So we have here the dot, and at another line, we have the dot on the top. The idea is here to decouple the signal, because the signal is in differential mode. So we decouple here the signal and incouple the energy going here to the powered device. And we have a transformer. This is the huge difference here. The signal is decoupled here by a transformer, And to block the DC voltage or the DC current, we have here this capacitor, and then you see here the center tapping, which is an impedance matching. On the secondary side, we go again to a transient protection and to the phi. So what I want to point out already, shown more in detail on the next slide, as we have a galvanic decoupling here, we have on the primary and the secondary side different ground connections. The PD is, let's say, mirrored here. The schematic here or the principle is the same at the PD size. So coming to the detail here a little bit, you see here this is the same schematic, the same figure as before. But you see here we have here a transient protection, which is the differential mode protection here on the primary side. And we have here at the secondary side after the transformer, here again a secondary transient protection, again which is in differential and common mode to clamp here and to protect the phi. So yeah, the galvanic isolation is standardized, but unfortunately, why do I hesitate a little bit? The PD is explained precisely by the IEEE standard and says there must be at least a 1 megaohm at 5 volt isolation between all accessible external conductors and the interface. The PSE is not mentioned there, but it is should be galvanically isolated as a state of the art, because in the end you have to follow the product safety standards. This is why the PD and the PSE should be galvanically isolated. You may know from this power over Ethernet standard that we have here a flyback converter or forward converter, which isolates then at the PD side the secondary side of this device for the power supply. But here you remember we have coupled all the energy only by inductors, meaning there is no galvanically isolation. So this must be additionally then taken care if you make this design. Yeah, the block diagram of our reference design. We have here again the power source equipment, and this is one example, one possible example. We have connected a Wi-Fi router because we have a 10 megabit Ethernet connection here. We have the incoupling of the energy of the 24 volt power supply. We have a USB 3.1 interface here, and then another one which is for, let's say, maintenance and checking and uploading the firmware, which is then a USB to serial converter here. Then on the secondary side, we go to the powered device, and we have again a 10 megabit Ethernet and a USB 3 connection. Okay, the block diagram itself, we come here from the single pair Ethernet interface, go through this magnetics I have shown you already, going to a phi, to the Ethernet bridge, then some magnetic interfaces for galvanic connection, and again via the Ethernet USB bridge to the port. Unfortunately, here we need then also this, let's say, this MCU controlled SPE, PSE controller. You need here a little bit firmware to give this controller a life and to fulfill the SCCP protocol by firmware. And we have here again the 24 power volt input. So, okay, the second slide here shows you an overview. There is the 10 megabit SPE board, which fulfills here the class 12, meaning up to 30 volt, 8.3 watt at the PD. We have the USB 3.1 port here or interface, no power on the board because this is not the purpose here. And we have a 10-100 megabit Ethernet port here. What is interesting, you can exchange data or transfer data, vice versa, this all or cross over this all interfaces, meaning from the Ethernet to USB, USB to SPE, or vice versa. And it works, but surely limited to the 10 megabit data rate. This gives you an overview of this PSE board here. Ethernet connector here, connection USB 3 connection. There we have two different possibilities to connect the single pair Ethernet, then the Ethernet bridge here, and the magnetics. What is interesting to show here is on the back side, you see a lot of TVS diodes, and here the gas discharge tube for protection in interference or transient protection of the interface. So again, a little bit detail here of this schematic of the PSE, and I have told you already that's the same at the PD side. But here we incouple the energy coming here from outside, from power supply, going through the controller, and is decoupled. Here again, decoupled in the higher frequency range, and going here through the common mode choke out to the PD. You see here from the other side coming inside, we have the gas discharge tube here to limitize the first, let's say, huge energy impulses going to the differential mode clamping here. And if the signal comes here inside, it is then transferred via this transformer here to the phi. Here we have a differential mode. Common mode clamping here. Sorry, that's common mode clamping here, going down to the protection ground. That's the primary ground of the system. By the way, these diodes here are so-called steering diodes to lower the parasitic capacitance of this TVS diodes here. You can read this detail in a reference design note. I don't have the time to go into detail what it is for. So the powered device here, almost similar at the magnetics and filter interface here, but we have here the PD controller, which couples in the energy, and we have here the onboard design for the 3.3 volt power supply. The Ethernet controller, magnetics interface, and going again to the USB 3 port. Good, here, the overview again, similar like as the power source equipment, but we don't have here the DC input connector for the supply. On the secondary, on the downside, again, on the bottom side, we have here the magnetics and the TVS decoupling and diode decoupling interface here. Yeah. Again, a little bit a different view of the interface. What is, again, important to know here, we have here the two different grounds, the shield grounding here for decoupling and absorbing the first, let's say, amount of energy in terms of transient protection, and going here to the secondary side where we have the ground system. And this one together gives you not only, let's say, a decoupling of the transients by high impedances, it gives you also a decoupling of all this, let's say, digital electronic in terms of radiated emission and conducted emission. Why? Together with the parasitic capacitances of this silicons here, you have a low pass characteristic. And this gives you then possibility with a, let's say, a limited filtering with capacitors. I have here quite good working reduction of radiated and conducted emission. Yeah, there's general design information to make it short here. There are layout considerations. Layout considerations which might not be the big deal when we go to the single pair Ethernet, but are definitely at the USB 3 and 100 megabit Ethernet, let's say, components or interfaces here. We need to have a differential mode pairs here, and they follow let's say, the rules which are shown here. So you must take care that the coupling of this differential pairs here is quite high to decouple to the let's say, to the other interfaces and have a good signal integrity working. Also, the ground fill, which is shown before on the layouts when you have seen the pictures here, the ground fill should not be too close to this to the single pair differential pairs here. Otherwise, you get a too high coupling and a disbalance here, and you have another mode of transmission. So these are some rules which you can see here summarized for you if you want to make such interfaces. Also, take care the dielectrica of this PCB, the layer stacking, because the dielectric permittivity, depending on which layer you look at, might be different to keep the signal integrity and that you have a good signal transmission. ESD protection, what is here to, the interesting point. Actually, Adrian will tell you more about this. The big challenge here is really over the long distance cables, the transient protection. And transient protection means if you have transients coming over the data and power line, or the single pair Ethernet line into the interface, you must absorb or lead the energy to the ground. This means each and every nanohenry or each and every, let's say, resistance, all these parasitic impedances to the ground are decisive if your system works or not. So you see here one example where how we use the TVS diode arrays. We lead them or connect them directly into the signal path and have the shortest possible way to the ground on the secondary side of the system or the shield ground on the primary side of the system. Why? You just imagine some energy comes here to the silicon, to the phi, or to the output of any interface. Only the output capacitance already of, let's say, 5 picofarad gives you a charge in terms of ESD discharge here, and will also cause a differential drop here via the parasitic inductances between the one and the other integrated circuit. And this is crucial here. Let's look at the other side here, or the next page. Only 1000 volt, 1 kilovolt of this, let's say, voltage difference already, and with a rise time of 1 nanosecond, so typical ESD discharge, gives you this 5 picofarad parasitic capacitance. This is the output capacitance of this device. Already inside this device, a charge or discharge current of 5 amps, which is too much. So the controller will be damaged. And in case of 10 nanohenry impedance, for example, with a 30 amp per nanosecond current, discharge current gives you already a voltage drop of 300 volts. So this is crucial. With this parasitic capacitances and inductances, you will damage the device. This means this clamping of this high transient voltages directly at the interface is crucial for the function here. And also then, how can I do it? Meaning this PCB must be connected directly to some metal housing, if you have one, or must be connected directly to the, let's say, clamping reference ground where your transients protections works to. Coming almost to the end here, meaning we have a kit. We have a kit which you may order, which you may buy at our homepage. Here it is like it looks like. It is the Poodle Class 12 30 volt 8.3 watt system with a 20 volt 24 volt power supply, which you can connect. There's a 1.5 meter single pair twisted cable, so this works on a single pair twisted cable, unshielded here. There are connectors inside, so the set is finished for usage. Sure, the firmware is already loaded on this device. So you have here the links if you want to have further information, and also how you can order and when you can order this set here. So that was a really quick, sorry for this speeding up, quick overview to give you an overview of the huge, let's say, content which is behind this whole system here. And then I hand over to you.
Yes.
Give you here.
Thank you very much.
Animal, the mouse, and
okay.
go on.
So then let's have a look on the EMC performance of this reference design. Since we are limited in time, we will focus on the emissions and immunity. So quick overview first over the boards. As Heinz mentioned, we have two different grounds. You have the shield ground where we can connect the shields, and we have the digital ground. So for this further investigations, we will connect the shield ground at the Ethernet port with 2 times 10 nanofarad and a parallel SMD varistor. And so more or less, we have something like a chassis ground. Also, same is true for this shielded Ethernet SPE connector, which will be also connected with 2 times 10 nanofarad and a varistor. For the USB 3.1, normally I connect the shield directly to the digital ground, especially regarding the immunity for at something like 2.5 gigahertz. You can get a lot of problems when you don't connect the shield. Quick overview on the test setup that we are using during the testing for radiated emission and immunity. So we have our fully anechoic chamber marked in blue here, and then we will have 2 notebooks. We will have one notebook in the chamber that is inside a shielded box and then connected with the Ethernet cable to our powered device. The powered device is connected with the SPE interface to the power source equipment. And this one is connected with a fiber optical Ethernet converter from MK to our outside Fritz box that is used as a DHCP server. And there we are using our second notebook as a client notebook. Notebook 1 will send speed and error packages, and we can measure them with the notebook 2. So we know during immunity testing if we have problems with the payload or if we get any errors. We will focus now on PSE, PD, and the SPOE line. We will use the Ethernet cables as shielded cables, Cat5e as a UDP, and 24 volts input here at a PSE. Quick overview on the software. So you can see we can measure the payload here on the 10 Mbits SPOE connection or PoE connection. So you can see we will have something like 8.5 Mbits payload. Rest is the overhead that you need for the protocol. And you can see that we can also measure the error rate. As a free alternative, you can, for example, use iPerf or JPerf. Now, how does this look like in the EMC chamber? Here you can see our small anechoic chamber in Waldenburg. We will have the PSE here and the PD there. In this case, we are using a self-made twisted pair cable. In this case, at least we have 1 meter of horizontal cable in the quiet zone of the antenna and the chamber. Our DC input cable will be routed inside the table in this cable channel here with 1 meter horizontal. And then we have also our Ethernet cable going down. Now, let's have a look on the radiated emissions. The radiated emissions in red are showed with a shielded cable and in green with only the twisted pair cable. You can see for both types of cable for the SPOE interface, we are far below the limit, at least 10 dBs, as you can see here. And more or less they are comparable. So we can see with shielded and unshielded cables, the emissions performance above 30 megahertz is quite good. Let's have a quick look on the conducted emissions. For the conducted emissions, we will only focus now on the PSE. Since the PD is easier to test, we only have 2 connectors here. So for the PSE, we will use a CISPO16 listen. You can see this one here. And we will connect the 24 volts input there and measure more or less the emissions on the 24 volt input line with these CISPO16 limits for the AC mains. Why are we doing that? So I would assume that we would pass also the limits and the tests for when we connect an external AC to DC power supply, at least for this electronic circuit, when we pass the same requirements with the DC input. So more or less, we assume that our power supply will not filter what is coming from our board. Then we will measure the SPOE line with a CDN T2 when we are using the twisted pair or self-made CDN SPOE shielded cable CDN. And on the other hand, we will have the CDN RJ45S for the shielded cable of the Ethernet connector. Let's have a look on the test results here. We start with the 24-volt input and on the CISPO16 listen. Here you can see the Class B limit lines for 230-volt AC mains. And you can see with the DC input, we are far below the limit on quasi-peak average. In this case, we are only showing the VCC results since the one for ground look more or less the same. So a lot of margin, that works quite fine. Then let's jump to the SPOE interface. SPOE interface, we are measuring shielded and unshielded. You can see that the emissions are a little bit higher when we are using only the twisted pairs without a shield. And when we use the shielded cable, the emissions are a little bit lower. But nevertheless, we are more than, you can see here, 20 dBs below the limit for the CISPO32 Class B for signal lines. So no issue here. And then finally, let's have a look on the performance of the shielded 100 Mbits Ethernet cable. And as we would expect, also we are far below the limit here. For example, also the 20 dBs. So we can conclude from emission point of view, the single pair Ethernet reference design and technology is working quite well. And we would not expect any issues in the field here. So then let's have a look on the continuous disturbances. Continuous disturbances are the conducted immunity according to 61000-4-6 and -4-3. 4-6, 150 kilohertz up to 80 megahertz, conducted immunity also called. And here we will pass the test with 20 volts for all setups with shielded SPE cable or also with unshielded cable. Let's have a quick look. How does the setup look like? We will have our device under test on the styrofoam 10 centimeters above the referential ground. And we have our CDNs with which we are coupling in common mode the noise. Here we have a CDN M2 for the 24-volt input. We have a CDN T2 for the unshielded twisted pair cable. And the CDN RJ45S for the Ethernet cable that is shielded. So then let's have a look on the radiated immunity test according to 61000-4-3. The result were that we passed the test with 20 volts, 80 megahertz to 1 gigahertz, and 1 gigahertz to 6 gigahertz with 10 volts per meter. So more or less also the increased industrial immunity requirements, and that was true for shielded, but also for the unshielded SPE cable. So, here the setup, again, same like for the radiated emission, the 2 boards, and in between we have the SPE cable. In that case, it's a shielded one. So passing here means that we pass with performance criteria A. So the payload is constant at above 8.5 Mbits, and we don't have an error rate, or the error rate is 0%. So, but we were not also only testing our boards and our design, and we also did some tests together with our friends from TI, for example, and we tested the TIDA board here with 10 base T1L, and the results were comparable. So we expect that the technology has a very good emission performance and also is very stable regarding the immunity testing. Then the single pair Ethernet is known, at least the 10 Mbits one, for a long distance. So we did some tests here. Again, now you can also see the notebooks that are running. Here we have our server notebook that is connected with the Ethernet cable to the PD. Then the PD is connected with a 100-meter twisted pair cable. You can see it here, to a PSE. The PSE is connected with Ethernet to the Fritz box as DHCP. We have the 24-volt input power supply, and the notebook is connected with USB 3.1 to the PSE. So here we are using also the hub as an Ethernet hub connecting here the DHCP server, the notebook, and the 10 Mbits file. So we were testing the speed. In this case, you can see no drop in the speed when we're using the 100-meter twisted pair cable. And I measured the DC voltage at our PD input, and we had a voltage drop of 1.5 volts per 100-meter cable. And now that is, I think, the limiting factor for this technology when it comes to single-pair Ethernet with power over data line. The very long, thin cable will give you a lot of voltage drop. And so more or less, this is, I guess, the limiting factor and not a SPE technology itself. So question is, when you use some milliamps here, how much voltage will you lose in your cable? So then I think 30 minutes, we're perfectly done.
Yeah, maybe we can tell that we currently work on the 100 megabit single pair Ethernet design, which will be most likely published spring of next year. And sure, once working, we will introduce you to this design again.
Again, yes.
Once I have passed your special high requirements, then this will be the topic for next year then. Thank you very much.
Thank you.
Yes, thank you for your interesting presentation. Quick information for you, the handout is now available and you can download it. And now we would like to turn our attention to the questions that came in. So I will start with the first question. How about reflection? Have you measured S11, S22 of your boards with spectrum analyzer?
We have measured signal integrity. We have measured the ports and the wave impedance, let's say transmission, yes, in the lab. This we have measured, yes.
Okay.
And this is within the, let's say, specification which is requested.
Okay, thank you. Okay, so next question. How define the PODL classes? Are there any specific components to meet PODL classes?
Yeah, there are. Yeah, let's start this way. You know, there is the SCCP protocol when the PD tells the PSE in which class you work. So this is the power consumption. So what you need is all the, let's say, the serial components like the common mode choke, the differential mode inductor. They have to fulfill the rated current. And the controllers at the PD and at the PSE side, you can use for higher classes. And then you have, I haven't shown this in the short time, there are MOSFETs, there are transistors which switch and lead the voltage, the supply, the current between the PSE and the PD. So the silicons, they have to fulfill the rated current, the maximum current. And this is actually, that's it. So that the components must be, let's say, capable to run the rated current. And then you have to program the PSE and the PD for the specific classes you want to have.
Okay, thank you. Next question. There is multi-drop SPE. Is this also possible with SPOE?
Not this design here.
Okay. Okay, then next question. What are the advantages of SPE with respect to PoE? From a product designer point of view, I'm interested in data rate, range, component usage mostly, and EMC performance design complexity. So the difference between power over Ethernet, standard Ethernet, and the single pair.
Yeah, you know, this is a long question, let's say, answer. Because power over Ethernet, the standard gigabit Ethernet, you need 4 channels, you need 4 pairs of wires, so you have 8 wires. And here you can also make the single pair Ethernet with 1 gigabit, but then the wires are shorter. You cannot reach this distance. So with gigabit Ethernet, you are more flexible with the hubs, and this is an established system already. But I think as time goes by or in the future, we will most likely develop the single pair Ethernet to the same, let's say, flexibility like the gigabit Ethernet we have now. So we will start, as mentioned, in spring with the 100 megabit, and the next design then will be the gigabit single pair Ethernet also, but then normally without power over it. But we will see if we can handle the power, because it's still, let's say, under investigation, this concept. Okay, thank you. So next question. The PD device has an SPE PHY, but there is no microcontroller on the PD device. How is the PHY chip configured? Yeah, at the PD side, you have only, let's say, some pins which you can configure that way that it shows the class. But the answer of the PD to set up the STCP protocol is always the same. But at the PSE side, you have to tell the controller which class you want to have, how the STCP protocol should work in detail. This is just, let's say, a circuit specific. The details, how this works, are explained in my reference design note. And in case you should have more questions, please contact me, because this is a long story to tell now.
Okay, thank you. Next question. Did you also perform a burst test with coupling clamp into cable?
Yes, of course we did. All the results are described in detail in the app note. I think it will be linked to this webinar. And the thing with burst is when you have this very long twisted pair cable without a shield, the burst testing is of course challenging. 1 kilovolt is possible, but above 1 kilovolt it gets challenging. And it can also happen when you are at 2 kilovolts that you get, let's say, an interrupt of the connection and you need to re-establish it. When we are using a shielded cable, we can go up to 4 kilovolts. But of course, I think the very interesting thing about a single pair Ethernet with twisted pair and the 10 Mbits is that we can use also unshielded cable on long distances. And then more or less we need to decide if it's possible to accept that we can have a link drop and we need to re-establish the link, or if we need to change to a shielded cable.
Okay, thank you. So next question. Why are you using a transformer instead capacitors in the SPE line?
Yeah,
good question. Good question.
The crucial thing is first of all the capacitive decoupling, meaning the higher the capacitance between the primary and the secondary side, the more you will produce common mode interference. And vice versa, the common mode, let's say, immunity will also drop. We have the transformers with quite low parasitic capacitance. This gives the big advantage that we have the decoupling between the primary and the secondary side. This is the signal decoupling. The power decoupling has anyway been done by huge inductors or inductances, which gives you a high reactance, high impedance. So this decoupling between the primary and the secondary side, this is the one thing which is important. The next one is the signal integrity. You have to follow what has been asked before. Have we measured the S21, S11, and this, let's say, the signal integrity parameters? You need the droop, you need the, let's say, the time, let's say, shifting between the low frequencies and higher frequencies, that it is equal. So the phase shifting of the signal should not over the frequency should be low. And for this, you need special transformers. So the signal transformers, they are especially designed for this single pair Ethernet. Yeah, and this is the one advantage. If you use the capacitive coupling, the biggest problem what you will have is, first of all, is the huge capacitive coupling between primary and secondary side. You need it. And the next thing is the symmetry. You get with all these capacitors an unsymmetry in the signal, which makes you then the problem with the immunity, emission testing, and signal integrity.
Especially for burst testing, the burst will be injected common mode on both lines with the capacitive coupling clamp. And when we have small differences or tolerances in the two capacitors in line, we will get a voltage drop, and then we will automatically get a problem with the burst testing. And it was also tested by partners from us and semiconductor partners in different technologies. So it is always challenging to use a capacitive decoupling in such signal lines.
So meaning for the 100 megabit design, we will have definitely different inductors. The whole magnetics will be changed to the needs for the 100 megabit, let's say, a frequency bandwidth, which we need. And for the gigabit, again, you cannot use this transformers for the whole range of data rates. They are dedicated for this bandwidth we need.
Okay, thank you. And last question, how did you connect separate grounds?
Yeah, in this case, we have only two grounds. We have the digital ground and we have the chassis or shield ground. And we will connect the shield ground to the chassis ground with 2 times 10 nanofarad. Best is on both sides of the connector to get a broader connection here. And in parallel, to protect the capacitor from transients coming from the cable shield, we use the SMD varistor to clamp the voltage.
Okay, thank you. So if there are any questions left, we will answer them afterwards via email. And yeah, we are finished now with our webinar. Thank you for your attention. I hope you enjoyed our webinar. Thank you, Adrian. Thank you, Heinz. And maybe also interesting for you, our speaker, Adrian, has today another webinar. The topic is the single wire IC LED under an EMC perspective, where you can now register. Thank you and bye.